Hello, everyone. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO. It's ACNOI. My name is Farid Char, and with the producer Hector Salas, we're going to be your guides during this trip to the ESO Paranal Observatory. So, just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010. And I have been working for an astronomy center in the University of Antofagasta, and I am very interested in astrophotography. But I am not alone. I am with the producer, Hector Salas. How are you, Hector?
Hi Farid, happy to be here. I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I'm working mostly with topics related to the CEM, the circumgalactic medium, and we can think of this as the environment that surrounds galaxies. And I have been a member of the team of guides for Paranal Observatory since 2019. I started while I was doing my master's in Universidad de Antofagasta. And today I'm the producer, and that means that I will be changing the pictures, the videos, but I will also be collecting all your comments and all your questions. So please, if you have any doubt, send a comment through YouTube, and during the tour we'll have some spaces to answer any question you may have. So feel free to send us any questions.
Yes, that's right. And I would like to mention also that this specific virtual tour is co-organized with the PICO project from Horizons Europe. So we are very happy to have all of you today, and you are very welcome to ask your questions. And we are going to be our best to answer all your questions and comments about this observatory. Okay, so welcome again. And we are going to start immediately with this virtual experience for all of you. And the first thing I want to do is to help you understand the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. So ESO is composed of 16 member states. The headquarters of ESO are located in Germany. Also, Australia has joined ESO, in this case, as a strategic partner. And Chile is the host state and home of all ESO observatories. Now, from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, you will see a picture with the three observing sites of ESO in Chile. So in first place, we have the Chacnactor Plateau, and this is the site of the ALMA radio telescope. ESO is part of this radio astronomy observatory alongside other international partners. Additionally, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And this one is using the HARPS instrument, and this is an exoplanet hunter. Finally, we have the place of our visit, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT, and this is the most advanced visible light telescope on Earth. But in the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope on the planet. Also, near there, the CDA will be an array of telescopes focused on capturing gamma rays. Okay, so now we have a better picture. So let's travel to the Paranal Observatory. So in this picture, we can, well, in this video, we are virtually flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital, Santiago. specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Daltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. So this mountain belongs to the coastal range, and despite its altitude, it's located at just 12 kilometers from the coast. And where's the ocean? Well, the Pacific Ocean is located below of this cloud cover that you can see in the distance. But why those clouds if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt Stream. So this is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. Above the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, we have other natural barriers again around this area. About 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. Now, the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean light pollution. So basically this is one of the best places on Earth for astronomical observations. Okay, right now we will change the view to have an even closer look to Paranal. So as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. So we are in the summit of Cerro Paranal. So in this place, basically we have an atmosphere that is extremely quiet. This observatory is a true oasis, and you will see how in one of the driest deserts we have a lot of life, but of course we have a lot of science. So right now we are going to jump immediately and visit the mountaintop. We are going to visit the summit of Paranal. Okay, so in front of us we have the Very Large Telescope, or VLT, its acronym. So if you pay attention at this screen, you can see some buildings, right? We have 4 giant domes right here and other 4 small and rounded ones. You see? So we have different telescopes here. Okay. So if you see this, it is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you will find the 4 unit telescopes, or UTs, each one with a primary mirror of 8.2 meters in diameter. Okay, so the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs. Okay, each one with a primary mirror of 1.8 meters in diameter. Now, coming back to the big ones, each UT here has a name in Mapudungun. Mapudungun is the language of the Mapuche people, the Mapuche culture, natives from central and south of Chile. So here, for example, we have Antu. Antu means sun in Mapuche. Here we have Cuyel. Cuyel means moon. This one is Melipal. Melipal means 4 stars, but this word is connected to the Southern Cross constellation. And this one is Yepun. Yepun is a reference to the planet Venus. So all of them have, let's say, astronomical names. And the closer ones here are the auxiliary telescopes. They are very special because they are mobile. So we can move the small ones using this rail system. You can see they have some kind of stations in the ground, right? So we can move the small ones to any station we want. And basically we have 30 stations in all this platform. So we can move the small ones up to 30 different positions because they were specifically designed to work all together as a single big telescope with a variable diameter. So the intention of all of this is to be able to reach up to 200 meters. So you will see a short animation right now to understand this concept. Here we are. So this technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. Now, thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So right now, we will come back to the tour screen. And here we are. So now you will have the opportunity to visit one of the telescopes. We are going to visit specifically this one, Melipal telescope, UT3. We can't enter to all the telescopes, but don't worry about that because the four ones are identical in size and shape. So the only difference are the instruments inside. So of course, if you want to know more about the telescopes and the instrument, you can take a look at the ESO website. Okay, so now we are going to access UT3. And here we are. Okay, so what can you see? Well, this is a giant telescope. It's very, very impressive. We are on the last floor of the telescope at the same height of the main mirror in front of us. The mirror is heavy, it's 22 tons with 8.2 meters of diameter and only 17 centimeters thickness. The mirror was created from a ceramic and flexible material. This material is called Cerodur. So I am going to do a close-up, and you can take a look at this mirror. So essentially the mirror, just for your information, the mirror is concave, okay? And the surface of this mirror is a very thin layer of aluminum. So this is not glass, okay? It's, as I told you before, it's a ceramic and flexible material. Its name is Cerodur. And the surface is a very thin layer of aluminum. So you need to understand that this telescope at night, you need to point this telescope to different positions in the sky, okay? You need to tilt the telescope, and of course the mirror will be tilted. And if you consider that the mirror is very heavy and is concave, the mirror will suffer some kind of distortions, deformations, just because of gravity, physics. So in order to prevent this kind of distortions and deformations, we need to do something. Because if you have deformations, if you have distortions in this concave shape, in this concave mirror, the quality of your final picture will be affected. So we need to do something about that. So I am going to explain what can we do in this case, but I need to show you this telescope from a different perspective. So I am going to change the view, and I can explain this better. So in this moment, at this moment, I am at the other level of this telescope. As you can see, I am in underneath, and I can show you the telescope from this perspective. So you can see there is something here, right? So this structure here is basically a cell. This white structure is a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some gray boxes. I am going to do a close-up. I can show you some gray boxes right here. Okay, so the gray boxes are called actuators, and they are a kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Otherwise, it will suffer deformations just because of gravity. And those deformations, even imperceptible to first view, could be critical in the result of the observations. So that's why we are applying this active optics system. Okay, so now I am going to explain a little bit how this telescope is working at night, because you need to understand that we have a very complex machine, and everything must work together in order to get information, the light from the stars. So now we are going to show you a short animation in order to explain this. Uh, so we have the animation. Okay, thank you. So the first step, of course, is to open the dome. Okay, of course, this is an exaggerated view. So we need to open the dome first. And the first thing is that we receive the light from the stars. This light is going to the primary mirror, the big one. The light is concentrated and reflected to a secondary mirror up there. The light is reflected again to a tertiary mirror, and this light will be reflected to one of the instruments. And we have three instruments in this telescope, three possible instruments. We have different instruments, in this case, symbolized by these red, blue, and red squares. But essentially, you have three possible options because you have a camera here, an instrument at this side. We have another instrument in the other side. It's not visible from this view. And we have another instrument in the base. So essentially, you have three possibilities. And each instrument is different. So we can use one instrument per observation, but the instrument will be different depending on the purpose of the intention of the observation. From this picture here, well, now you know that this is the primary mirror, 8.2 meters. The secondary mirror is there, is this one. This is a convex mirror. And the tertiary mirror is not visible from here because it's essentially in the center here. But it's not visible because we have a structure blocking the view. Okay, so essentially you have three different mirrors, and they will be collecting the light, reflecting the light, and the instrument will receive the light and will essentially convert this physical light into a digital signal. Okay, so during the day, as you can see this picture was taken during the day. During the day, we have some people working in the telescope. We have, for example, engineers working. Okay, and these people is working to calibrate, to do calibrations, maintenance, fixing problems. they are doing different kinds of work in the telescope during the day, but during the night, the work is for astronomers. Okay, so essentially, that's the daytime work at Paranal. During the night, the work is for astronomers. Okay, so this is essentially what happens here. I am going to finish the explanation of the telescope at this point, because the next stop of this virtual visit is the control room. This is essentially the workplace for astronomers, and because the astronomers are not here at night, they are not inside of the telescopes. They are working from a separate location that is very near, but is in this specific facility, in the control building. The control building is a very special building located just next to the telescopes, and here you can find the workplace for astronomers. But before going there, maybe we have some time to check if we have some questions from our virtual visitors.
Okay, Farid. So we have a lot of comments in the chat. They seems to mostly be greetings. Thank you for giving you greetings. And a lot of them are in what I think is Greek, which I cannot really read. So please, if you have any questions, please try to send it in English. And in the meantime, I'm going to ask you one of the usual questions that we get in the virtual tours, but also in the in-person tours to Paranal Observatory. What kind of maintenance is necessary to do to the telescopes?
Yeah, sure. It's a very good question because, well, of course, the most important and delicate part of this telescope is the mirror. So when you need to do some maintenance here, in the mirror, you need to apply two kinds of maintenance. One of them is like a simple maintenance, and you need to do this essentially like once a month, and you need to tilt the telescope a little bit, and a couple of engineers will spread a carbon dioxide snow on the mirror. So this carbon dioxide snow is something like a foam, and the intention is to remove dust because we are in the desert, we have dust in the environment. So this carbon dioxide will remove dust, and because the mirror is tilted, everything, the dust and the carbon dioxide will fall to the ground by gravity. So that's what happens for the easy maintenance, and this is necessary only once a month. But every 2 years, we need to do a more complex maintenance. And this complex maintenance requires to extract all the mirror from this building. I mean, we need to remove the mirror and the wall base right here. We need to do this with a special crane, and we need to extract the mirror using a special door here. And in order to understand what happens after that, I want to show you a picture from the outside. And you will see, for example, that next to this telescope, there is something here, right? A yellow structure. So essentially, we need to place the mirror here, and at the ground level, we have a vehicle waiting for the mirror. So this structure will essentially drop the mirror very gently, of course, and we need to place the mirror in this vehicle. So the vehicle will transport the mirror down to the base camp in order to um, essentially place the mirror in another facility to do a process that is called a recoating. The recoating is essentially a process where you need to remove the aluminum layer with some chemicals, and then you can put a new one, a new aluminum layer. So essentially, it's like change to a new mirror. Okay. Well, of course, the core material, the zero dur material, is always the same. You are only changing the aluminum layer. Okay. So after this process is finished, after 3 or 4 days, we can transfer the mirror again to the telescope platform. We can lift the mirror, and we can reinstall the mirror in the telescope again. So the telescope will be ready again for observations. So that's what happens in order to keep the mirrors in optimal conditions. And this is very important because all the mirrors are the original mirrors from uh, more than 20 years ago, because Paranal was inaugurated around in 1998. So Paranal has more than 20 years of operations with the same original mirrors.
Okay, we have a couple of questions now. Uh, Here they're asking us, why do we need to build such big telescopes?
Excuse me, sorry.
So
Well,
this,
yeah. Um, well, if you want to understand why we need to build bigger and bigger and bigger telescopes over time, is because, well, the main reason is curiosity. Because when you want to understand the universe, at some point you need some kind of more advanced instruments. And in astronomy, when you think about telescopes, if you want to observe fainter objects, um, difficult to observe with our current technology, with our current telescopes, you essentially will need a bigger mirror, a bigger kind of instrument in order to capture the light, because what we are talking about optical telescopes. So in order to get more light, you need a bigger mirror. You need a bigger collecting area of light. Okay, so in I don't know, maybe in the 50 years ago, telescopes of 4 meters, 2 meters, or something like that. This was the best size. Okay, but for example, in the beginning of this century, 8 meters or 6 meters mirrors were more the standard. And at this time, in this decade, we are expecting to finish the next generation of telescopes. That's why in next to near Paranal, we are building the new extremely large telescope, and this will be an almost 40-meter mirror. Okay, and near the Coquimbo region in Chile, we are building also the GMT, the Great Magellan Telescope, 25 meters. So as you can see, in order to observe more difficult things, fainter objects, you need to increase the mirror size when you are talking about optical astronomy, optical astronomy. So that's the main reason. Now, I don't know, Hector, if you want to comment about that.
yeah, just to give the simplifying version of all what you already just said. Uh, a mirror is this is like putting a bucket in the rain. The larger the bucket, the more water you can capture. And this is the same. The larger your mirror, the more light you can capture, and therefore you can see things that are fainter, and they could be fainter because they are intrinsically fainter, or because they're much more farther away from us. And we're trying to observe even fainter things every time because we want to expand the frontiers of the knowledge in astronomy. Now we have a bit more technical question. What is the focal length of the biggest telescope and the maximum magnification? Do you have the number, Farid? Because I was looking for it, and I found that the focal length
Oh,
is
sorry,
about.
sorry. Yeah, sorry. It was with my mic off.
You are muted.
Yeah, sorry. So the focal length is about 120 meters or something like that.
That's right. I was looking for it and
Yeah.
I found
Okay.
122 meters. So probably
Okay. Yeah.
120.
Yeah. Yes. Yes. So this is because you need to consider, in order to know this, the telescope mirror diameter and the focal rate, the focal ratio. This is about f15, if I remember well. So yeah, the result is something like 120 meters of focal length.
Okay, and we have one more question. We have one more question that we're going to answer now, and then we'll continue, and then we will have another part for answer more questions. So the final question is, why are the telescopes are located in Chile?
Well, because as I was explaining at the beginning of this virtual tour, in the Atacama Desert, we have a lot of different specific conditions that are very unique, uh, like a clear and dry atmosphere, clear skies. We have the Humboldt Stream in order to block the clouds from the Pacific. We have the Andes Mountains blocking the clouds from Argentina and Bolivia. So essentially, you have something like a bubble of um, good conditions for astronomy. And these kind of unique conditions are, let's say, available in a few places on Earth. For example, in the southern hemisphere, yeah, the north of Chile is one of the top places for astronomy. You have only a few other places, maybe South Africa, maybe Australia, but the north of Chile has the most concentration of telescopes because of the conditions of the Atacama Desert. In the northern hemisphere, you have Hawaii and Canary Islands as the top places for astronomy in the northern hemisphere. So essentially, in the southern hemisphere and in general, the north of Chile has a very, very good conditions for astronomy because of the natural environment of the Atacama Desert.
Yeah, and in addition to that, it's also a place where we can build the telescopes. Like, for example, Antarctic has very good conditions for doing astronomy, but building something there is very difficult. So that is also another consideration. And Chile was trying to attract astronomical observatories at the time. Okay, so we're going to continue, and we're going to have a second round of questions later. But before we go, are we going to see pictures from space? Yes, we will see a couple of them. So now you can
Yeah,
continue for it.
that's correct. Yeah. Okay. So we are going to continue, and I am going to show you something very interesting now. This is the control building, and I will show you now the control room. So the control room is essentially the workplace for astronomers. And as you can see, is like an office space. You have different workstations with different computers for different purposes. And each workstation belongs to a very specific telescope. So this workstation, for example, belongs to Melipal UT3. So only operations with Melipal are from here. If we take a look at the opposite workstation, this workstation belongs to UT4, Jepun. So only operations with Jepun are from here. And again, you have some terminals here, you have some people working, and all observations will be supervised from here, okay, from the UT for the UT4. If we continue working through this corridor, I can show you the additional workstations. This workstation here is for ANTU. Okay, so only operations with ANTU are from here. Okay, and we have a few terminals, have people working, the same arrangement. And here we have another workstation, but this one is for Cuyen. So essentially, and to understand better about this place, the telescope, sorry, the control room, the Paranal control room is the place to do the remote control of the telescopes and all the systems I explained before. So if I show you this workstation, for example, if I go here, side, you can see the same arrangement, and you will find two specific people here. You will find a telescope operator. This person is a telescope operator here, And the telescope operator is essentially in charge of the technical details and the movement of the telescope. So it's like the pilot of the machine. But the ESO astronomer is the person in charge to direct the scientific observations and will decide the next steps. So it's like the co-pilot. Okay. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. And each night you will find telescope operator and an astronomer per telescope. Okay. So that's it. This is the main purpose of the control room. It's not extremely futuristic, but you need to stay here all night from sunset to dawn in order to do all the remote observations of the telescopes. Okay, I am going to come back now because at this point I know that you know a lot more information about the telescopes and the scientists working here. But now I want to show you the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So let's take a moment to take a look at this top 10 of the more interesting milestones from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so that was the top 10. I hope you enjoyed. Now I will do an interesting activity, because usually when you go to Paranal as a tourist, you can do it during the day. Okay? But here I can show you some of the most interesting portions of the night sky from Paranal. So, for example, in this real picture, you have some very interesting regions and objects. So I can show you a few of them. So you have, for example, this is the Antu telescope. And here, for example, we have a very popular constellation. This is the Orion constellation. In Orion, you can find those 3 stars somewhat aligned, and they are representing Orion's belt, because Orion is it was a hunter, mythological hunter. Okay, so the 3 stars are representing Orion's belt, and next to Orion's belt, you have another interesting object, and this object is the Great Orion's Nebula. This object is very bright, it's very big, is possible to observe even with your naked eyes in a clear and dark night. You can see it like a distorted spot, okay? And you can observe this object with some binoculars or even a small telescope. So it's very, very popular for observers in the southern and the northern hemispheres. Now, if we continue moving from Orion up, we will find this, the brightest star in the sky. This star is called Sirius. Sirius is the brightest star of the sky, and this star belongs to another constellation that is called the Canis Major. This is one of the hunting dogs of Orion. Okay, so this constellation is connected in the mythology to the Orion constellation. Okay, now if we continue and I show you something here next to Antu, we have another interesting object. This one. This is an open star cluster. The name of this cluster is the Pleiades. So the Pleiades is a very popular object also for amateur astronomers. You can observe, even with your naked eye, you can observe up to 7 bright stars here, and that's why in the mythology you can call this object something like the Seven Sisters. Okay, Now, this open star cluster is located in the constellation of Taurus. And if you pay attention to this area in particular, all this region here is, you can find more concentration of stars. Do you see? So we have much more stars in this area if we compare with this area, for example, or this area. This is because all of this is one of the Milky Way arms. And in this case, um, this is a very beautiful area, of course, and you have a lot of different features, such as the dark clouds, which you have some nebulas, you have a lot of different bright stars, and well, typical objects located only in the southern hemisphere. So essentially, all this area is much more interesting in the winter. I mean, the winter in the southern hemisphere, because you can find the center of the Milky Way. I mean, another area very populated with stars, but belonging to the center of our galaxy. But again, is only visible in the winter times, or winter months in the southern hemisphere, such as June or July. Okay. Okay, I will move quickly to show you something else. We have two interesting spots here. Those spots are the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. They are galaxies. They are not clouds exactly, because those objects were recorded by Ferdinand Magellan during its circumnavigation of the planet in the 16th century. But of course, at that time, no one had any idea about what a galaxy is. So those objects were recorded as clouds. But now we know that they are irregular galaxies, but they are also satellite galaxies of the Milky Way. So they are orbiting our Milky Way. Okay? And the last thing I want to show you here is the smallest constellation in the sky, the Southern Cross, right here. This is also visible only from the southern hemisphere, and you can see that the shape is similar to a cross. In this picture in particular, the cross is tilted. Okay, so you cannot you cannot see this straight up cross, but this one is the Southern Cross, and this one is the smallest constellation in the sky. But again, this is only visible from this hemisphere, and if someday you are in Chile, in the north of Chile, it will be very easy for you to identify this constellation and of course the Magellanic Clouds, because they are very, very beautiful and very clear in a dark sky like this. Okay, I am going to come back because I need to finish with this virtual tour, but the last stop for this virtual tour will be the residence, and I will change the view to the daytime because I have to rotate the view to visit the base camp of Paranal, and I will show you a very special place here that is called the residence. What is the residence? It's essentially the place for the ESO staff. Okay, it's the place for rest. We have the bedrooms for the ESO staff. I mean, for the engineers, for the astronomers. They can spend a few days in this place. Okay, the residence is not exactly underground, but it looks like underground. So you need to use this ramp in order to access the residence. And I will show you the inside. It's essentially a very beautiful place, and that's it. You have a swimming pool, you have some green areas, you have 108 rooms here. So it's a very big place. But again, even if this looks like a hotel, it's only for the staff. It's not for tourists. But you can find all the necessary stuff for them. You have a restaurant over there. You have a reception. You have the reception. You have the lobby. So you have everything same like a hotel, but in this case, it's only for the staff. Okay, so I know I am running out of time, but I think we have some extra time for to answer the last questions. Hector?
Yeah, we have several questions. So let's start by this one. How would the combined power of the smaller telescope compares to the power of the larger one?
Well, when you combine the telescopes, I mean, when you do interferometry, you are essentially simulating a virtual larger mirror. And in the case of the big ones, for example, if you combine two telescopes, okay, depending on the distance, for example, if you have one telescope separated from this other telescope by, I don't know, like 50 meters, you are essentially simulating a virtual telescope of 50 meters. Now, the maximum distance between the telescopes is 130 meters. So you can essentially simulate a virtual mirror of 130 meters. And in the case of the small ones, the maximum separation between the small ones is about 200 meters. So essentially, you are simulating a virtual larger area. But this interferometry system is very useful to get more details on bright objects, okay? Because you don't have a real bigger collecting surface. You are simulating only. But this is very interesting and very useful to have a better spatial resolution. So that's why we are using interferometry in Paranal.
Yeah, and just to clarify, what we meant with resolution here is that if two stars are very close together, with low resolution, we see them as a single star, but with high resolution, we can see them as two separate objects. And for what I was looking at, the increase in resolution doing interferometry can go between 17 to 25 times better resolution, depending on the configuration you're using. Okay, do we have more questions? There are a couple of questions on that some people are already answering in the chat, so I'm going to skip those. You have another question here. What is your favorite things about the telescope, and how do you decide what to name them?
Well, maybe the most interesting or funny thing about the telescopes is that they are able to work together because this is actually a very unique feature. This is what makes Paranal the most advanced optical telescope on Earth. So this ability to work all together is is very special. It's like it's a challenge, of course, because you need to do a very precise and accurate, let's say, alignment of the light rays because you are combining the actual physical light, and this is a very difficult challenge. So I think for me, this is not only amazing; it's only a, I don't know, a very interesting example of how the current technology, even if we are talking about technology from 20 years ago, right now is still very, very impressive and is enabling important scientific discoveries. And regarding the names, there was a contest some time ago where ESO was proposing a series, different sets of names, and one of the proposed names was the Mapudungun names. Okay? Actually, these names were proposed by school children from, I think, Calama or a place in the Antofagasta region. But it was actually a contest. So a person from I mean a school children was able to name the telescopes with these Mapudungun names.
All right, I have a question here. Do you seek for exoplanets?
Well, regarding the search for exoplanets, I think the 3.6 meter telescope in La Silla is more dedicated to do that because they have a very specialized instrument to search for exoplanets. I think from Paranal you also can do it. You can do, for example, this detection with the exoplanet transit system. And I think there is a new instrument that is specialized and is doing actually that, right?
I'm not entirely
Right, I
sure,
think.
but given the characteristic of Paranal, it's probably better suited to do follow-ups on exoplanets than actually actively seeking new exoplanets, because we have a lot of instruments that can do that. We also have some satellites that are specifically dedicated to that. Like TESS, I think was the last one that was sent for that. But yeah, we can observe exoplanets. That's something we can definitely do.
Yeah, of
We
course.
have
The follow-up is also important.
Okay, one question. Many observatories on Earth or in space are starting operations now. For example, Vera Rubin, Euclid, or James Webb. Do they observe the same objects? Is there some complementarity?
Well, when you have a different telescope, of course, it's always good to have a lot of more telescopes to do more observations. But you need to understand that some astronomer is at some point applying to observe at some of the telescope, and this observation comes from a proposal, a very specific proposal. Okay, so and this proposal was probably evaluated for 6 months or something like that. So it's not like you are always combining observations or observing the same things. You have a very strict, um, let's say, application time to apply for telescope time. So essentially, well, strictly talking, you are not observing the same things, but in sometimes when you have a very specific event such as a gamma ray burst, a supernova, or whatever, sometimes you have, for example, a space telescope able to observe something like that, and you have like an automatic alert sent to all observatories on the planet. So in case some of these observatories are in a good position, are in a good location with their, of course, at night, and you have and you are able to point your telescope to that specific object, yes, you can eventually do a combined observation of something very, very interesting. But this is something like an exceptional telescope time. Okay, it's something that is officially called the target of opportunity. But in the regular conditions, all different telescopes are observing different things, unless you are working in a kind of, I don't know, like a very specific observation campaign, and you need to combine observations from this telescope and this telescope and this space telescope. But in normal conditions, all telescopes are observing different things. We hope all of them, each of them, have a specific, I don't know, call for proposals, and they have a specific and independent projects going on.
Yeah, and just to complement a bit your answer, for example, like the Rubin Observatory is more of a survey telescope, so it's producing maps of the entire sky every other night or so, and then you can use that to look for things that are moving or changing in brightness. And there are some areas that astronomers like to observe. For example, the Hubble Deep Field that was later observed again from Paranal with Muse, for example, and it was later observed with James Webb. And it's a particular area of the sky that has been part of very detailed and very good set of observations. So people like to observe it again to see what else we can find of the many, many galaxies that are there.
Yeah, that's
Okay.
correct. Okay, I think we need to finish because uh,
Mhm.
we're past
Okay,
our time.
so we are reaching our limit. So, and There are a couple more questions, but they're in Greek, and the only one that I managed to translate was, do we study dark matter? And yes, we do some observation that could study dark matter and dark energy. And with that, I will say goodbye. It was my pleasure to be with you here today. We'd like to comment that we are also doing this. This was an extraordinary tour, but we're also doing regular virtual tours on Saturdays, both for the Sea Observatory and Paranal Observatory, alternating between both of them, and English and Spanish. So if you want to join to one of those, please keep an eye on ESO social networks.
Yeah, that's correct. So thank you very much to all of you for watching our virtual tour today. Thank you very much, and I hope to see you maybe in one of the regular tours on Saturdays. So on behalf of ESO, I want to say thank you again, and I hope to see you someday in Paranal in a public visit tour. Okay, so thank you very much and goodbye. Have a nice day.